Hello, everyone. I'm Marc Hamilton, and I'm excited to be here today as the host for NVIDIA's special address at SC20. This is a different SC20 with it being fully virtual, but it's nevertheless very exciting. We have three from NVIDIA today that are going to talk and explain how NVIDIA is powering the change in scientific computing that really is expanding in all directions. We'll start off with Ian Buck. He's our Vice President and General Manager for Accelerated Computing at NVIDIA. Following Ian, we'll have Charlie Boyle, VP and General Manager of our DGX systems. And finally, very excited to introduce for the first time at SC in the role of NVIDIA's CTO, Michael Kagan. So with that, we've got a lot of material, so I'll hand it off to Ian to get started.
Thanks, Mark, and thanks everyone for joining us today at SC20. It's a different SC20. I've been coming to supercomputing for over 20 years. I've never come to it from home. I guess in the time of COVID, everything's a little bit different. But it's never been more of an exciting time, I think, for high-performance computing, for supercomputing, when we're looking at how our supercomputers, our HPC algorithms, could be applied to some of the biggest problems facing us today. And of course, the threat to humanity of COVID. Drug discovery in general has inspired much of the work that we do here at NVIDIA and in the supercomputing industry to figure out how our computers can be used to help understand and discover new drugs that can be applied to our problems. If you think about the whole entire pipeline for computational chemistry and drug discovery, it's rich with computation and the opportunity for computing to make a difference. It literally takes $2 billion to market it and take a drug from concept to deployment as a treatment for a disease, often 8 to 10 years. And sadly, with over a 90% failure rate on new drugs that tried. By using computation to help fight and understand those algorithms and how drugs can be applied to those, all the way starting from the initial search for literally the billions of chemical compounds known to humanity that can be used to fight drugs, to narrow that down to only a few tens of thousands of candidates, to understanding their genomics, their molecular structure after the genomics folds and performs the structure, the docking of how those two things interact, and the simulation of actually the biology and how it's built and how it comes together. And finally, the imaging and the effect it has on the human body, and even all the way back around to the research published. Today, neural networks like BioBERT are used to study all the documents, all the publications across all of medicine, modern medicine, to help create structured data that we can search and mine for new opportunities. Sadly, COVID has figured out, and biology has figured out a way to make new kinds of virus, one that is definitely damaging and harmful for humanity. And sadly, it may not be the last. But I am excited to see all the great work being done to actually apply our computing capability and our prowess as a community to help fight this disease and understand it better so that we can aid in its treatment, discover vaccines, and hopefully prepare us potentially for the next pandemic. With that, I'd like to show you a little video. This is work done with Oak Ridge and others to help understand the COVID molecule and how it affects. And it really gives you a view of what computational chemistry and supercomputers can be a computational microscope. So with that, why don't we roll the video and let's enjoy it.
Weighted ensemble simulations at scales never before achieved show us how the spike actually opens. And what's so important about that is knowing the pathway of opening presents new opportunities for drug design. One can start to imagine finding molecules that will trap the spike in particular conformations to halt the infection process. We then extended this work and used artificial intelligence-based workflows as a multi-scale glue to bridge key capability gaps in terms of the spike protein at the next level of complexity, as it forms that critical handshake interaction with ACE2. What was really key here was having the AI learn information at the smaller scales in order to drive the conformational sampling of the spike within the more complex scene. This enabled a speed-up factor of more than 8x relative to standard approaches. Stepping back, thinking about all that we've accomplished in these 8 months, it is like climbing a mountain. Sometimes it feels like you're never going to make it, but then you get to that summit and you look out and just, wow, what a view. Seeing things for the first time, discovering things that no one before you ever even imagined. That's really what this is all about. And looking out from this new vantage point, it's so much easier to imagine a bigger, better, and brighter future for HPC and the world. Thank you.
Though this may be difficult times, it is truly amazing to see supercomputers become the computational microscopes we've always dreamed them to be, to where they can actually show us the biology happening in real time in a way that wouldn't be possible, but only in science fiction. And with the introduction of HPC and AI together, we can make those simulations happen in timescales that show biology in action, so we can have an understanding of how this disease works. As you may have already heard, the Gordon Bell finalists have already been announced, and many of their contributions to science not just recognize the scale of the simulations they're doing, but also the impact they're having. And many of them are obviously focused on COVID this year. We just showed you a deep drive MD, which in combination of NAMD is showing a 350 million atom simulation of one of the largest molecular simulations ever. This used the 27,000 GPUs in the Oak Ridge Summit supercomputer to both simulate and render those results. The Deep Drive MD has been downloaded by over 4,000 researchers worldwide, to help create drugs to help fight COVID. In addition, there's been a lot of other great work. Docking analysis, for example. This is also work done with Scripps and Oak Ridge to study how different chemical compounds could intercept and dock with that COVID spike to limit its progress or interrupt at the key moment when it affects the cell. Using GPUs and working with NVIDIA researchers at Scripps and NVIDIA, together we've helped port Autodock to CUDA and accelerate that workload by over 50 times to run that much faster. In addition, we've incorporated Rapids with our Blazing partners at Blazing SQL to help with the search for chemical compounds that can actually perform to study those results. They've ordered some of those chemicals in wet labs now, and I'm looking forward to seeing some of their results, if any of them can be used to fight the COVID disease. DeepMD is another example. This is actually simulating the quantum forces all the way down at the molecular level. Molecules are made up of atoms and bonds executing extreme forces and immense velocities. Modeling the quantum effects of that is paramount. And by using AI, they can actually assist those simulations and speed them up by over 1,000x with the same accuracy. And not just AI, but data science too is having an impact. SKA, the Square Kilometer Array, will be one of the world's largest telescopes when finished building. And it'll also be one of the world's largest big data projects, generating literally terabytes of data. Using GPUs, we have some hope of actually processing the data to find the anomalies and the things in our cosmos that we've only yet dreamed of witnessing. It's a foregone conclusion that the simulation combined with AI, combined with data science, is the path forward for HPC and scientific computing in general. And that's how NVIDIA we think about it. The new expanding universe of scientific computing, with a combination of simulation, AI, data science, as well as computing at the edge, and of course visualization as well. Doing all those things inside of a data center can give us the opportunity to understand where the scientific discoveries need to happen. At NVIDIA, we've been focusing on innovating in all these spaces to build data centers that can perform these tasks. And today, NVIDIA's AI supercomputing leadership, it focuses on bringing all these components together and making them open and available to you in the community. Today, we obviously have been focused on simulations and supercomputing with our latest products. Today, we're over 11x higher performance in just 5 years. From the original P100 GPU when we shipped in 2016 to today's A100-based supercomputers, we've improved HPC performance by 11x. Even in the time of Volta, when we shipped it back in 2017 to just recently, That same hardware that was announced, those same supercomputers, got 2x faster, more than 2x faster, because of the work that we did together as a community to accelerate and figure out how to accelerate science by using accelerators to advance the research. In the new workload of AI, nothing's better than the NVIDIA GPUs for running number one in MLPerf and the MLPerf benchmark, a benchmark created by Google to help understand and measure the performance of the different AI platforms. We just came through the round of AI training and inference and achieved number one in that platform. We also, in terms of data science, are delivering better TCO for data science customers. On this retail benchmark, comparing to a CPU to a V100 GPU published back in December, this 10 terabyte data set benchmark, which is a combination of SQL and ETL operations, is delivering 19x TCO, 19x savings because of the benefits that GPUs can bring to their customers. And of course, this morning, I hope you all saw the news on Green 500, where we're achieved DGX SuperPod, which Charlie will talk about later, achieved number one energy efficient supercomputer on that list. And NVIDIA also powers 8 of the 10 top supercomputers, delivering that super energy efficient supercomputing performance that was identified so long ago. It was a supercomputing community that first recognized the end of Moore's law, that realizing that the path that they were on, we're going to have to build supercomputers that are the size of city blocks and consume as much power as the cities in order to achieve the performance they needed for their simulation. By taking those first steps, the steps by Satoshi at Tokyo Tech or Oak Ridge National Labs with the Titan supercomputer, they help pave the way for this future. And I thank them very much for their initial deployments. And we can see it today. Today, however, we're on a totally new path for supercomputing, one where we're at the center of era of exascale AI supercomputers, where computers today are not measured by their HPL performance, but by their performance on simulation, but also on AI. And if you plot the growth of AI supercomputing, you can see it's on a totally different curve than the rest of the community. HPL continues to grow and is an important part of science because it measures our simulation throughput with FP64. But AI is the new tool for doing our science. And now today's supercomputers are measured on their capability of being exascale AI supercomputers. The first one announced was the Summit supercomputer, which was used in many of these Gordon Bell announcements. And today, sharing some of the news out of Jülich with their supercomputer, 2.5 exaflops of AI, and the Leonardo system, 10 exaflops of AI. The world's largest supercomputer announced to date. Very exciting results. Even Fugaku and the work being done on ARM is amazing. And some of the science already coming out of these supercomputers is exciting as well. As a result, science has gone to exascale. We've seen results from the climate work for simulating atmospheric rivers using neural networks. This was done in conjunction with researchers ourselves. We designed a new neural network which can measure and actually predict atmospheric rivers in the atmosphere, working with Berkeley National Labs, 1.3 exaflops. The work on genomics with opioid addiction at Oak Ridge, it delivers 2.3 exaflops of AI to understand the genomic backgrounds of opioid addiction to help fight this terrible disease. Nuclear waste remediation was work done actually to use AI to predict and understand the subsurface strata. Unfortunately, at this site where they have potential contaminated materials in the ground leaking into the groundwater. Understanding the subsurface strata was only possible and actually minimize the number of physical probes they had to insert in the ground by using AI to predict and data science to predict the subsurface strata and how it flows. And finally, cancer detection. 1.3 exaflops, again, at Oak Ridge and Stony Brooks. Here, this is based on the Mendel framework, which was actually looking at medical data to perform and do cancer predictions 16x faster than traditional methods by looking at individual slides of biopsies. There's over 200 million biopsies per year, and traditional methods of classifying them and identifying cancer or non-cancerous cells just can't keep up. But with the advent of AI, we can actually do comparable accuracy to humans and aid those cancer specialists to understand those diseases and process this important information quicker. At NVIDIA, our contributions, again, not just our researchers who join in these exercises to help design those neural networks, help working with our customers to actually figure out how AI can be used for their simulations, but we're also developing new products to help people deploy AI. Not just training, which we all know TensorFlow and PyTorch and the performance that we've been working to make sure that they get the best performance on their supercomputers for building neural network models, but also deploying them. One of our most recent software packages is Triton. Triton is a neural network software which is used to actually deploy a neural network in production. It operates as a REST server and can execute the neural network in the data center in real time. Users configure it as a simple server. They point it to a neural network model, and then it acts like a REST interface. So a simple HTTP or gRPC request, give it your vector of data, it runs the neural network and gives you the result back. It sounds really simple, but inside of it is actually a very complicated piece of machinery that's managing the GPU resources. It's actually can serve thousands of requests in parallel from different users, different applications, different models, all at the same time to maximize GPU throughput. As a result, this is actually being used today for things like credit card fraud, for image recognition, for some of the consumer and popular web applications that you're probably using on your phone today. What's so interesting is actually it's being used by HPC developers as well. Work done at Fermilab is using Triton to actually detect neutrinos. Neutrinos, these invisible pieces of matter that are flying through us all the time, but because they have no charge, they're incredibly difficult to detect unless they happen to collide just at the right moment with an atom and environment, and we can detect those collisions. Fermilab is actually using Triton to detect whether those interactions, the data coming off their detector, is an actual neutrino hit. And by moving it to Triton, they ran it on a bunch of T4 GPUs to process all that data and improve their performance by over 20x versus what they had before, and processing over 400 terabytes of images. Super exciting work, and the same technology that's being used to run AI for credit card fraud or recommend pictures on your phone is also being used to detect neutrinos. We've made Triton available. It's open source. You can download it today. It supports TensorFlow models, PyTorch models, Onyx models, even custom models with TensorRT. It supports GPUs. It supports also CPUs. There's no reason, if you're using inference, please go down and download and enjoy and try Triton. So for the next generation of supercomputers out there, we're now in the era of exascale AI supercomputers. Super excited about the work being done at NERSC, at ULIC, certainly the work at ABCI. All the new GPU-based supercomputers are hitting new levels of performance for the HPC, including the Leonardo supercomputer, that with its 10 exaflops of AI performance announced earlier last month. Very exciting work. Also super excited about the progress on ARM. NVIDIA, as mentioned, is in the process of acquiring ARM. We're super excited about that. ARM is the most ubiquitous CPU platform in the world. I'm surrounded by ARM devices today, and they bring great joy to many people. They're the most prolific CPU platform in the world. NVIDIA being the leader in AI technology, we're excited to bring those two technologies together and bring AI to ARM's ecosystem. Today, HPC is very excited about the work being done on ARM. I'm very pleased to see the work done at Fugaku on the Fugaku system based on the Fujitsu ARM-based CPU. The work being done to understand humidity and the effects of humidity on transmission of COVID in environments is eye-opening in terms of how easily are differences in the spread of COVID-19 right now. And in addition, we've actually been benchmarking other ARM processors out in the community, including the AWS Graviton, which actually is performing 20% faster on applications like GROMACS, Milk, and NAMD than the traditional x86 systems that are being deployed, that I see deployed today in supercomputing. So ARM is ready for HPC and supercomputing, and we're ready there to help advance it. Today, we're actually investing heavily in that ecosystem. So we've been working with optimizing for SVE and the compiler stack there. That's available in the A64FX processor that's used in Fugaku. We also are working with all the cloud data centers to bring GPUs to their ARM platforms as well, most notably Ampere Computing and the Marvell Thunder X series. Of course, we've always been involved in ARM from an edge and robotics standpoint, which obviously is a huge install base, and we've actually been building processors there for a long time. And even interest in the PC space, where people want to put ARM-based cloud gaming. We've been bringing our entire software stack to ARM as a result, and many of it is ported today. In fact, we're seeing already sort of exponential growth in performance in ARM over time. Just a year ago, when we were benchmarking the early ARM system to today, we're seeing a 2x improvement in ARM CPUs and HPC applications. And then, of course, with GPU applications on top of it, we're getting over 25, 26x more performance by integrating a GPU with that ARM system over time and transitioning from Volta to Ampere. So we're super excited about that future. We're working with everyone to try to help get there sooner. I encourage you to, if you're discussing with NVIDIA, share your perspective on ARM, which applications need to be ported, what parts of the ecosystem are you most concerned about, and hopefully we can work together to get those platforms ready on ARM. Well, in addition to the work we're doing with exploding data with ARM and HPC, earlier this year we announced Ampere, the new A100 GPU. With it, we've seen great adoption. But of course, the application use cases for it have not slowed down at all. Today, we're seeing massive growth again in the data sets people want to process, whether it be simulation or AI. Today, 90% of the world's data has grown in the last 2 years. We're now clocking over 50 zettabytes, getting up to 175 zettabytes in just 5 years' time. And some of the results that I've already shared with you, they already represent literally terabytes of data in order to perform these simulations. SKA alone is going to generate 16 terabytes a second of data to be processed. The same is happening in AI. So in the AI space, which we obviously track very closely, some of those neural networks for machine learning and natural language processing, which is really the heart of intelligence, human language, are very large. You have to capture everything, not just what I'm saying, but what I mean, and come up with an answer based on everything they've learned from the internet. Obviously, those neural networks are quite huge. As a result, we're constantly challenged to connect as many GPUs together and to build the world's largest GPUs to serve those workloads. So with this drive, we're excited here at Supercomputing to announce that we've already refreshed our A100 GPU to now include new memory technology to achieve 80 gigabytes of HBM memory. That 80 gigabytes, the new NVIDIA A100 80 gigabyte is supercharging the world's high-performance AI supercomputing. Using a new HBM2E technology that was previously 40 gigabytes, we now have double the size of Ampere. In addition, this new memory technology is faster. Previous A100 was 1.5 terabytes a second of bandwidth. We're now achieving 2 terabytes per second with HBM2E. Combine this with it's the same Ampere A100 GPU with its great third generation tensor core, which brings together training, inference, and HPC, as well as the multi-instance GPU capabilities, effectively giving you 7 GPUs in one, each being the performance of Volta. And of course, our third generation NVLink. Perhaps you can go to the next slide for me instead of me clicking the controller. Thank you. As a result, A100 is actually as amazingly fast. This GPU actually delivers over 300 teraflops of FP32 training. Using our TF32 technology, most neural network models which are trained with 32-bit floating point today automatically get the benefits of this technology. As a result, they're seeing over 300 teraflops of performance. TF32 is now default in TensorFlow and in PyTorch shipping today, and developers of AI need to make no code changes at all. They simply will experience the benefit of our tensor core directly out of the box, delivering 312 teraflops of performance for FP32 training. That's a 20x improvement over Volta and making it the world's fastest training GPU. Secondly, it's also a great inferencing GPU with over 1 petaOP of Int8 performance. This is used for some of the fastest inference technologies, inference deployments today. Again, another 20x higher, making it the world's fastest inference GPU. And finally, for HPC, Tensor Core now has FP64 calculations at full IEEE. That's delivering over 19.5 teraflops of HPC performance, making it the fastest HPC GPU as well. A wonderful universal GPU for AI, for inference, and for HPC. And now, of course, with 80 gigabytes, is now, of course, is the world's largest GPU from a memory standpoint and the fastest from bandwidth. Next slide, please. We've measured the new 80 gig on the HPC applications, on HPC applications, and because of its larger size, we're often seeing nonlinear speedups. It's amazing. So, like for example, simulations for some of the largest data sets run 2x faster. This is based on a basket of applications that we've seen that want to do the calculations in core than managing potentially out of core calculations. In addition, those big data problems, the 10 terabyte retail data set I saw achieved another 2x performance. For recommender systems, this is for AI training. Recommender systems are some of the world's largest neural networks. Remember, recommenders are trying to take every product on the internet with every user and train that neural network. Those are obviously very large neural networks, very large problems. They could benefit greatly, seeing a 3x improvement. And of course, with a higher memory bandwidth, going from 1.6 to 2 terabytes a second, we're getting our MIG inference instances are just getting that much faster. And as a result of being able to do things in core, you've seen the results on Green 500. We now have been able to achieve over 25 gigaflops per watt of performance. And that's because we can move that HPL calculation to an in-core calculation, moving the computation to where it wants to be run and most energy efficiently. So with that, next slide, we can see that we've refreshed our platform yet again. And we call it the HGX platform. Originally designed for hyperscalers, we're seeing adopted in supercomputers and all the next generation supercomputers that I mentioned today. And we'll have more product announcements coming up. HGX really stands for hyperscale and high performance computing. That same HPC capability, that universal tensor core with training, inference, and HPC is now available to supercomputers everywhere. It's also available in the cloud and runs all of our software stacks. So HGX is a great platform for that convergence of HPC and AI, and it's the building block for the next generation and the era of exascale AI supercomputers. Next slide, please. And the great news is it's available everywhere. So we have all of the clouds bringing HGX A100 online today. We've already had announcements from pretty much every major cloud provider with early access, or some are actually in production today. We also have systems coming out now from all the major OS vendors here in the US and Europe and all across Asia as well. Super excited about its adoption and and seeing it finally in the market. And I hope you too are getting a chance to try it soon. Next slide. We ourselves, of course, are practitioners of AI. NVIDIA is developing self-driving cars for our customers. We use AI to optimize our production and, of course, help you and work with you as researchers and have our own AI-based exascale supercomputers to help develop and plot that path forward. That system's called Selene. That's appeared on the top 500 a couple times. We have since refreshed Selene now and the team took all the guts out and refreshed it with the latest HGX platform, now with the A180 gig, and the results were amazing. It's now number 5 on top 500 published this morning, achieving also making it one of the greenest supercomputers in the world as well. Built from that DGX SuperPod, which Charlie will talk about later, makes it incredibly energy efficient. This is the same system we use for MLPerf, proving that it's a great supercomputer for HPC and AI supercomputer. It's also the world's #1 industrial system. It consists of about 4,000 A100 GPUs, and you can see the specs there. Most importantly, it's delivering 2.8 exaflops AI, and actually a fairly small footprint, only 560 servers. So to go more into the details of this system and the products it's built on, I'll hand it off. I think it's important, before I do so, it's important to note, everything we do at NVIDIA is open. We make all of the software that I've talked about today available on our NGC portal, all the AI frameworks, the Triton software, all the work that we've done with optimizing and containerizing the HPC applications we make freely available to you. So please go to ngc.nvidia.com. You can search and explore both our HPC application containers, our AI work, as well as the visualization packages in PowerView and others. You can download, run it in your Kubernetes environment, or crack that container and pull the bits yourself. We try to make everything freely available. In addition, the systems themselves, the components and pieces that make up Selene are available to you as well. Either you can buy it directly from us as a DGX product, or buy it from one of our many partners around the world that build supercomputers. We build it, we battle test it, we use it ourselves, and then we make the entire stack, including all the hardware components available to all of our partners to activate it worldwide. And of course, including the networking gear as well. So all these specs are open. So it's an exciting time in supercomputing. Never before, I think we've seen so much technology transfer happening, from the systems to the software to the new ways of deploying it to the new problems we're having to solve as a community. So with that, let me hand it over to Charlie. Charlie, you can explain a little bit more about some of the products that we've been announcing and how people can enjoy them.
Thanks, Ian, and thanks for everyone joining us today. Let's go to the next slide so we can just get started with the greatness here. Super proud of the team on the Selene build. In the middle of COVID, while we were doing everything remotely, they upgraded the Selene system. As Ian just talked about, one top 5 placement on the top 500 list. And that was all done with off-the-shelf products. The DGX A100, the new system that we're announcing today, the A100 640 gig system. Our existing system that Selene previously was based on was our 320 gig system, but with our latest GPU advancements, with our new HBM2E memory, with the incredible capacity and speed that we have, we are now shipping the largest GPU memory footprint that we've ever shipped in a DGX system, 640 gigs in a single system. Now, when we double the GPU memory, we have to make the rest of the system better too. We've doubled the system memory, we've doubled the cache space that you have, and we've added another redundant CX6 card to it to just make it an incredible system. And as Ian pointed out, just doubling the GPU memory doesn't give you just a 2x improvement. In many applications, we see beyond a 2x improvement because you can fit the entire problem space into GPU memory. The DGX systems have just been great for our customers. We've deployed these all over the world in super pods and in custom research pods, up to 3x overall performance improvement on this new system. Just an incredible machine. And as we look at this machine, we see it as a foundational building block, whether you're building a supercomputer system, whether you're building an AI training system, whether you're doing mixed inference, whether you're doing data science. When we built the A100 generation of systems, we wanted it to really be that universal building block. So no matter what workload you have, you can run it on the same infrastructure and then just scale your infrastructure. You no longer need infrastructure silos. So whether you're building that out of DGX systems or building that out of one of our great OEM partner systems, the A100 building block is just phenomenal for all of your accelerated computing needs. So let's go to the next slide. Now, we've been shipping DGX for a number of months now, and as I said, we've seen tremendous customer uptick on this. When you look at how this system physically appears on the screen, you can see it's a modular system. We built this system knowing that we could upgrade elements as they were ready, as technology improves. So for all of our existing DGX A100 customers, they'll be able to upgrade with a simple tray replacement and upgraded memory and drives in the system. So, building on that, brand promise of DGX, not only do you get the latest and greatest technology as soon as possible, but we build it in a modular framework so that as we come out with new technologies, you can keep that same DGX platform, and we give you in-place upgrades on that. So we're super excited that the engineering team was able to pull it off technically, and we'll be sharing more details in the coming month of how customers can take advantage of this upgrade system. The existing systems are great and they work fabulously for the users that have them, but if they want to get to the latest and greatest, we definitely have a way to do that for you. And with this new system, it's just twice as effective in so many areas like MIG that you can get so much more use out of the system. So let's go to the next slide and see how customers are actually using these systems. As we look at our SuperPod, as Ian talked about, a single scalable unit inside of SuperPod is now #1 on the Green 500. And as you look at these racks behind you, you say, wow, they're not really that full, and they don't have to be full to give you great energy efficiency and fantastic performance. And that's what the SuperPod solution is really all about. It's a blueprint and a design, but it's far more than that. Internally, we've developed this as a product. So everything Ian talked to you about in Selene, you can buy as an off-the-shelf thing from us. Whether you want something as large as Selene or as small as 20 nodes, we can give you that SuperPod design. And beyond just the reference architecture, you literally sit down with our engineers, spec out how many systems you want, and then you draw it out in a rack elevation, and we customize everything from there. We've got a great team inside of our networking group that actually does all of your custom cabling. Our system integrators do a fabulous job rolling these systems in. So you can literally order a SuperPod, and we've seen this a number of times in the last few months. And between the NVIDIA team and your local system integrator, they're shipping you fully built racks that you literally plug in a few cables and you're up and running with your SuperPod. Just a fantastic way to get supercomputing quickly and scale quickly. For those of you that have tracked us for a while on the top 500 list, you saw that not only did we upgrade the Selene system with the new 80 gig GPUs in it, we've also expanded it. The SuperPod solution allows you to start small at 20 nodes and grow to thousands of nodes if you need it. So just a fantastic option to get people up and running quickly. So let's go one more slide. As we look through our users, and we talked about this at GTC just a month or so ago, one of the SuperPod systems that we're building for NVIDIA and to help the overall research community, especially in the medical areas, our Cambridge 1 supercomputer. When we announced it, we couldn't tell you that it was going to be the 640 gig versions because we hadn't announced that yet. But I can now tell you that the Cambridge supercomputer, along with a number of our other SuperPod deployments, will all be the new 640 gig system. We actually started shipping this last month in the month of October. One of our SuperPods that we previously announced, the University of Florida SuperPod, was the first customer to receive our brand new 640 gig systems. We have more customers getting them this month. So at the end of the show, call up your local system integrator or NVIDIA sales rep, and you can get these brand new systems as quickly as you need them to do the great work, to hopefully solve COVID more quickly and to do all the great science that all of you are looking at out in the community. So let's go to the next slide and talk about something that you guys really didn't expect us to announce. You expected after Ian's presentation that I was going to tell you we had a new 80 gig DGX, but we have something really cool and interesting coming out for you guys that has amazing uses in scientific computing, supercomputing everywhere, AI research, and it fits under your desk. So let's play the video because the video can show you a lot better than I can talk about it. So just a tremendous achievement from our engineering organization across the board in mechanical design, electrical design, thermal and cooling, our brand new DGX station A100. If I put the side panel on this, it would look like our existing Volta system, but this is so much different internally. We took the same HGX four-way board that Ian talked about that's in the world's fastest AI supercomputers. And through the miracles of engineering force and compressing things together, we actually have that same HGX four-way baseboard in a workstation form factor that sits next to your desk. 2.5 petaflops of AI performance. 320 gigabytes of GPU memory sitting next to you. We talk about this as a workgroup appliance because this is something that you can share between all of your users. This is the only desk side system available, and probably that will ever be available, that runs our MIG technology, our multi-instance GPU, which you see on all of our data center servers. And that allows you to share a single DGX A100 system with up to 56 individual partitions. The DGX Station A100 is exactly half of that. So you can have over 20 users around your organization and around the world connecting to this system, doing collaborative work together. While this looks like a workstation form factor, it sits next to your desk, it's ultra quiet, but it has an amazing amount of power. With that MIG technology, I can be running multiple experiments during the day with all of my collaborative work group on what the best possible experiment is. And then all night long while we're sleeping, run massive training runs on all 4 GPUs, all running full out with NVLink, with something that can plug in anywhere in the world. So in the term of COVID, in the time of COVID, I should say, many people aren't in their offices and they don't have access to new data center space. You have to solve problems, but maybe you can't get into your data center. Maybe you can't build out data center space right now. The DGX Station is an awesome solution for that. It can be shipped to your office. Anyone could plug it in for you, literally add power and networking to it, and it's fully remote manageable. The same remote management features you would expect on a high-end server, we've put into this DGX Station. You can train bigger models. You can do more work with this. And at the same time that you saw in the video, we've moved from liquid cooling to refrigerant cooling. And at the same time that we've gone to refrigerant, we've been able to use a non-toxic, non-flammable, completely maintenance-free setup. So just a tremendous feat of engineering. I wish I was at the supercomputing show in person and you guys could touch one of these things, but I can assure you it's awesome. And just an incredible feat of engineering, bringing the power of a supercomputing node to something that sits under your desk. So let's go to the next slide. And as we think about supercomputing terms, as I said, this DGX Station has the exact same HGX board in it that you're building the world's largest supercomputers out of. So once you've made the decision to build a new supercomputer or expand the supercomputer that you have, what's the very first question your users are going to ask you? Well, when can I get the first node so I can start doing my software development, my software porting? Well, you may not even have the data center built yet. You may still be working on physical construction. The DGX Station, because it's the exact same setup as you would be putting in a supercomputing node, obviously using a lot less power because it has to plug into the wall, but the same software that Ian talked about, the same software that works across our entire ecosystem, the same software that you port and develop on a DGX Station will run just that much faster when you actually get your supercomputer built out. So whether you're a research group, whether you're a data science group, whether you're building a new supercomputer, the DGX Station is going to get all of your users productive that much more quickly as you build out your next generation infrastructure. It's just an incredible product and an incredible way for users to speed up their development. So once you turn your supercomputer on, you're not spending 6 months in software testing and development. You can turn it on and then just start optimizing your software. So let's go to the next slide. When we look at performance compared to the existing DGX Station, that was a fabulous product, a one-of-one product in the market. We're 3x, 4x the performance of that system in the same physical chassis. It's the same box from the outside, a lot different on the inside, but still running at only 1,500 watts of wall power. So it plugs in anywhere in the world. So, a 4x improvement in performance per watt is just incredible. And if we look at the next slide, the current station has been adopted across all industries, all sectors. And the feedback that we get from customers is it's just amazing because I plug it in, turn it on, and it just works. I'm productive the same day. And that's really a testament not only to the hardware design that we have, but as Ian talked about, that one NVIDIA software platform that runs across everything. And that's so important for our users. They plug it in, they turn it on, they get an NGC container, and they get fabulous results the same day, not weeks or months later. So that's the end of the DGX section. Super proud of the team. The Selene team probably needs a rest right now for making it to number 5 and getting us in the number 1 spot in the green 500. I'm super proud of everyone that worked on that. I wish I had another 10 minutes to thank everyone personally. But hopefully the team is resting this evening for their great achievements. And now I want to turn it over to Michael Kagan, who has some incredible news and advances of how we're taking networking and supercomputing to the next level.
Okay. So let's talk about the supercomputing. And so first of all, the high-performance computing requires high-performance I/O. And the first comes the network speed. Advanced InfiniBand and Ethernet network technologies and products actually designed to meet data delivery to meet the processing power of the GPU. The rule is simple. The higher processing power of the compute element, the more data it can process, hence the faster data delivery is required. The fast data delivery is just one part. Efficient network interfaces that are required to keep computing going. RDMA GPU direct technologies enable direct communication between GPU-powered computing elements and the cluster, offloading network overhead to the network itself rather than using application processor. Storage access is yet another bottleneck that needs to be resolved, and Magnum IO GPU direct storage seamlessly utilizes capabilities of advanced networking and enables data transfers at line rate between storage server and the GPU computer. Entire scale-out computer is architected and designed as a holistic platform. In-network computing elements like Sharp processes data as it moves. It executes operations that require high fan-out or fan-in, which removes the hotspots or software complexity caused by the execution of such an operation on the network periphery, which is endpoints. Last but not least, this is architecture of software-defined computing platform. Data processing unit on the compute nodes institute infrastructure computing platform that virtualizes all data center resources. It orchestrates application processing, manages cluster resources, and provides full isolation and security. I'll discuss DPU in a component in a few slides later on. The Magnum IO delivers high performance, and here are some examples of performance improvement by the Magnum IO software stack. The first one is the parallel HPC application for atomic scale materials modeling. This is simulation of base physical phenomena, calculating electronic structures and quantum mechanics dynamics. This application is accelerated by NVIDIA GPU using customized nickel mid-layer. Application performance is boosted by about 50%, more than 1.5x, compared to the plain MPU software stack. The second graph in the middle shows improvement of segmenting extreme weather phenomena like hurricanes from climate simulations. At last, the rightmost graph shows performance improvement of file storage of almost 4x by using GPU direct storage. Today, we are announcing NDR, the 7th generation of infinible network solution. Let's take a look at new capabilities that open up by new generations of InfiniBand, looking at the video.
To most people, NVIDIA Mellanox InfiniBand doesn't mean much. But changing the world means a lot. To most people battling a disease, the impact of 2 times faster data throughput isn't obvious. But getting their medical analysis twice as fast means everything. And to astronomy enthusiasts, innovations like 4 times higher MPI performance with new in-network computing engines might not spark the imagination, but finding the right path to land on Mars does. If you would ask people living in small villages about 5 times higher switch system throughput at 1.6 petabits per second, You might not get them thrilled, but tell them they could get a hurricane alert on time, and you've got their attention. To most visually impaired people, 6.5 times higher scalability connecting more than 1 million GPUs at 400 gigabits per second may not seem to make a difference. But being able to operate an autonomous vehicle probably will. In these challenging times, 32 times more AI acceleration power with NVIDIA Mellanox Sharp may not mean much to many of us. Accelerating supercomputer processing to help the world fight a pandemic faster should mean a lot. Introducing the 7th generation of NVIDIA Mellanox InfiniBand, now at NDR 400 gigabit per second speed. The world's only in-network acceleration platform with ultra-low latency. For the supercomputing community, it means the world.
Great. So this new generation of infinible network solution includes all elements required to build high-performance network. The network adapter, both NIC and the data processing unit, capable of delivering 400 gigabit per second bandwidth on a single network channel. High-capacity network switches up to 64 ports of 400 gigabit with the built-in computing capabilities and all interconnect products, full range of cables from passive copper to optical cables. These components provide full network solution for next generation supercomputer. Faster computing requires faster network. The new generation of InfiniBand technologies continues to set world records. It is 7th generation solution. It delivers twice faster data throughput than current products. It has advanced in-network computing accelerations along with fast network provides MPI performance boosts MPI performance by factor of 4. Bandwidth capacity of NDR switches for this generation switches are 5 times higher than the current generation. And director switch provides 1.6 petabit per second bidirectional bandwidth on 2000 network ports at 400 speed each. Supercomputers become more affordable. Advanced topologies enables NDR network to connect more than 1 million nodes on only 3 hops, which is 6 times faster scalability. The improvement of sharp technologies of in-network computing will accelerate neural network training by factor of 3. And the NDR generation will create new opportunities and enable new capabilities of supercomputing and artificial intelligence. This is the network solution for exascale. So the higher performance enables actually saving the money by utilizing these new technologies. And using NDR interconnect to build cluster of 1500 GPUs will cost about 20% less and will consume about 20% less power. So overall saving of power and TCO is 1.2x. However, when you go to and build a computer of 4,000 GPUs, actually it becomes even more effective. It is almost 50% more effective than building this scale of the machine using the HDR, the 6th generation technology of 200 gigabit per second. So now we have entered the era of new paradigm of data processing. Data processing moved from von Neumann machine paradigm to data flow paradigm. Data is being processed on artificial neural networks that are designed into every appliance or gadget. Neural network required for real-time inference can be afforded in appliances like cell phones or smartphones. However, training of this network requires supercomputing power. As a result, supercomputing services become a commodity requirement, similar to computing services became commodity requirement a few decades ago. So in the near future, everyone on the planet will have its own custom-trained neural network. Everyone on the planet will be a customer of a supercomputer to train his own custom network. Hence, next generation of supercomputers needs to be architected and designed as cloud-native platforms, service delivery supercomputing platforms. Supercomputers need to be designed to deliver bare metal services, support multiple tenants running on the same machine concurrently, like in the cloud environment today. These machines must be built to deliver full protection of infrastructure as well as confidentiality of users and their data. These machines must be designed for software configurable service delivery. All this must be accomplished with no performance compromises, at zero performance penalty. After all, performance is all supercomputers are about. So traditionally, supercomputers are designed as for massive scale-out applications, and access to these machines are limited. Software running on these machines is certified, and in many cases, entire machine runs a single application. Performance is an ultimate priority. In cloud environment, security and isolation are the first priority. Initial developments of virtualization technologies actually came with a very high performance toll. And with time, this toll was reduced by offloads and accelerating solutions. We designed the new architecture for supercomputing that delivers secure supercomputing services without performance compromises. Cloud security standards with supercomputer performance standards. This is the combinations this is the combination that our architecture will deliver. Zero performance toll. We design cloud-native supercomputer architecture to be used to build next generation of supercomputers. The base of this architecture is Bluefield DPU, data processing unit, that constitutes infrastructure computing platform. This computing platform is designed to run all virtualization software and data center management and provisioning, offloading this task from the host processors. Moreover, DPU provides full infrastructure security and customer data confidentiality. Bluefield DPU enables to bring confidential data to supercomputing cloud. Bluefield-based supercomputers will enable cloud computing as a service, will enable to use supercomputers to serve hospitals processing confidential medical records. So Bluefield DPU is the platform for cloud-native supercomputer. Traditionally, the cloud computing runs all the infrastructure processing on the host processor. Bluefield is infrastructure computing platform, and it is designed to run all infrastructure management and provisioning, executing all tasks associated with the data delivery, and providing full solution and full isolation and protection of infrastructure and customers' data. Bluefield integrates the most advanced network adapter, storage and security accelerations, and actually brings artificial intelligence acceleration to infrastructure computing. Storage is a special case for the high performance, presenting local storage as a virtual service running on the Bluefield. Storage provisioning and allocation is done by Bluefield transparently, by software running on Bluefield, transparent to the application and without any interference with the CPU. Bluefield enables to deliver local storage performance over the network with zero performance cost on the host. Protected data computing is yet another challenge. And Bluefield enables to run application on cloud supercomputer processing confidential data. The data is encrypted and transferred between the client storage to secure enclave on the supercomputer under Bluefield control. Only trusted application, signed application on the host can access data on this in this secure enclave, which enables to process confidential data on the cloud supercomputer while maintaining full data confidentiality. In addition to infrastructure isolation and data protection, Bluefield accelerates the application performance by executing MPI communication framework and the entire Magnum IO software stack, offloading the application computing tier to run the application. It is particularly important for GPU-powered computing that enables direct clustering between GPUs on multiple nodes. The data is moved between GPUs while control plane is executed on the DPU, removing the host processor from the network IO and IO control paths. So the Bluefield DPU is the cloud-native infrastructure platform. CPU, GPU, and DPU are three key pillars of the cloud computing. DPU is an essential pillar for cloud supercomputing. It enables to deliver supercomputing performance in protected and isolated cloud environment. DPU-based supercomputer can be used as HPC service providers. Institutions that build supercomputers like academia can provide supercomputing services to scientists, healthcare, and other academia institutions. We are looking forward to work with ecosystem partners and customers to deliver supercomputing cloud solutions. HDC certified software packages will be available on the HDC repository for our customers to build cloud-native supercomputers. So we are getting to the era of exascale computing, where AI, artificial intelligence, becomes a mainstream data processing paradigm. Artificial intelligence processing will be available on every appliance, every device, and every gadget for real-time data processing to generate insights. And every device will use we will use is going to have embedded neural network capable of real-time inference. Inference can be afforded on the gadget. Training of the neural network is much more compute-intensive task that requires supercomputing that consumers will not be able to afford. Yet, neural network on personal devices needs to be trained using personal data. Everyone on the planet will become a consumer of supercomputing services that can only be delivered in the supercomputing cloud. At NVIDIA, we are designing the architecture and develop platform, reference design, and software for cloud-native supercomputing. This architecture will be base for all supercomputers built in this decade. So that concludes my talk, and we can move to Q&A.
Thank you, Michael. We're probably going to start the Q&A with you since we know it's very late where you are. But it's just been an amazing year when I think back to supercomputing last year. In the last 12 months, we won ML Perf with our Volta-based SuperPod, previous generation. Over half the year, the entire company was working from home, as was much of the world due to COVID. We, of course, completed the acquisition of Mellanox. Thank you, Michael, for being our new CEO. And we announced the acquisition of ARM. We then went off and we launched the A100. We launched DGX A100 earlier this year at our Spring GTC. And now only 6 months later, we've refreshed that and come out with the new DGX A100, doubling the amount of memory. On Green 500 and Top 500, we've improved in only 6 months, improved the energy efficiency of a Top 500 supercomputer by 25%. Think of that, an instant 25% savings in your power bill, instant 25% savings in your carbon footprint. And of course, all the work that we've done in networking, the DPU launch, and then going on today to NDR 400 gig. So we'll start our first question with that, Michael. I think this one actually came from someone on the Selene team, but it said, when will NDR 400 gig products be available?
That's going to be available early next year. First, before middle of next year, we'll introduce our first NDR products.
Great. So by SC next year, I expect we'll have a few interesting results to show. Second question, also related to NDR. How does that? Of course, we understand how it's going to help HPC, but how about AI? Can you speak a little bit about how faster, lower latency InfiniBand will help accelerate AI?
The AI is all about the data flow and the performance, and not only 400 gigabit of the link, but also advances of the in-network computing and the GPU interface to the network will enable overall AI performance accelerated by 2 orders of magnitude, well, 1.5 orders of magnitude. That's what we expect from NDR network. So faster throughput, lower latency, and more in-network computing and more efficient network interfaces. Combination of all those.
Great. So, I'm sure our software teams are hard at work getting ready for upgrading CUDA, CUDA-X, all of our frameworks to take advantage of the improved capabilities in NDR. Shifting gears a little bit on questions, here's one for you, Charlie. You talked about the DGX A100 system being upgradable with the new 80 gig GPUs. Can you upgrade an old DGX station that had the Volta GPUs in it?
Thanks, Mark, for the question. Unfortunately, you can't. That's still a fabulous system. It's got 4 of our top end V100s in it. But as you saw from the video, the radical new design that we have, the refrigeration system, now that we've moved to an HGX full baseboard in the system, it's not possible to upgrade. That system is still a great system, and we're looking forward to all the great customer feedback on the new design.
Okay. Let's see. Let's take a question for Ian. You talked a lot about our leadership in AI and in winning MLPerf, such an amazing benchmark. Can you comment on our standing in HPC?
Well, we've always been investing in HPC since for my career, over 15 years in NVIDIA now. At this point, I think the results you can see in the list in the top 500, 8 out of the 10 top 10 supercomputers in the world use NVIDIA's technology. We also have over 1,800 applications now accelerated with GPUs. I believe over 800 of them being simulation and HPC. So on top of that, we have over 2.3 million developers on our platform, really giving it the install base that people can invest in and deploy in HPC. I'm really excited to be at the forefront of the new technologies that are going to revolutionize supercomputing. Certainly AI, which you've seen some great results with everyone. It's a real joy. Many of my conversations at supercomputing have been about how can I figure out or apply AI to my problem? Where do I get started? We try to make that as easy as possible with NGC, putting all of our software stacks, all of our components on NGC, certainly. And then also the future of next generation supercomputers with ARM and GPUs. So we look forward to that future. And I think the future for HPC and NVIDIA continues to be strong and bright.
Okay, we're going to switch back to Charlie. Charlie, I think in addition to AI performance, I think that the interest in DGX from supercomputing customers has also grown as exponentially since last supercomputing, at least by the questions. But could you talk a little bit more about how the new DGX Station A100 complements the GPUs that customers have in their supercomputing center?
Yeah, to great question. It's something that we really strived for in the new platform, to really take the same technology, the same GPUs, the same software stack, and put that in the station form factor. So for anyone that's building a GPU based data center, you may have hundreds or thousands of nodes in there. The station affords your users, your data scientists, your researchers, an ability to work in a smaller work group to develop their experiments, to be efficient, collaborating together, not tying up, large cluster resources. And then as their research, as their experiments are more mature, then they can more efficiently run those experiments on your very large cluster. So the two products are very complementary. And the nice thing that we were able to achieve with this system, since we all use the common HGX board, whether you're buying DGX systems for your supercomputer or whether you're buying one of our great OEM partner systems, they all use the same HGX board. So you get consistent performance, consistent feature sets. The MIG is the same. The software revisions are the same. So you can easily move work that you've developed on a DGX station to your supercomputing cluster, whether that's a DGX cluster or whether that's a cluster, built out of our great OEM components.
A few more questions for you, Charlie, if you don't mind. This one, the question was a little bit ambiguous, so maybe answer it for both products. When is the new DGX A100 available? So why don't you answer for both the new DGX A100 system as well as the DGX A100 station?
Sure. The new DGX A100 system, our server-based system, we've already been shipping. We've been shipping them quietly because we had to wait till today to announce them, but that product is shipping. So if you call up your local NPN partner, you call up your local NVIDIA sales rep, you could put an order right now and get it in standard lead time. So the server's already shipping. It's what's in Selene. It's fully in production. The station we're still working on a little bit. It is real. Everything that you saw in the video team actually had a real station that was there for it. The team is finishing up some software and some mechanicals on it. We expect the station to be shipping the first version, the 320 gigabyte version, to be shipping towards the end of January, and followed probably about a month later with the 160 gig version.
Well, Charlie, I'm sure a lot of our customers in data scientists will be happy to hear. I know my engineers at the company are going to be really happy to hear because, somehow with along those use cases that you said, I know all of my solution architects have a GPU in their laptop. They, of course, everyone that works at NVIDIA has access to thousands of GPUs in Selene and in our other systems. And I still get lots of requests for a DGX station. It's one of the favorite systems for our engineers internally. But I know we promise we'll ship them to customers first. Going back to multi-instance GPU or MIG, how does the new DGX A100 80 gig, how does that benefit MIG?
Yeah, so the MIG instances just got twice as powerful, twice as effective. So whether you're using the server product, your single smallest MIG is now 10 gigs. I mean, that's a great Jupyter notebook. That's great for inference. It's also great for starting your training. So on a single system, a single DGX A100 server, you could have up to 56 MIG slices on it. Obviously, you can have smaller MIG slices with more core counts and higher memory available, but MIG is just super useful. And as I talk to customers, it's the number one feature they want to talk about, whether they've started using it, whether they're planning on using it, to be able to dynamically turn on the MIG technology and be able to switch from a single 8-way complex or a single 4-way complex, and then to slice individual GPUs up to hand out to users. I mean, Mark, Ian, I know you've heard this from customers for years. The thing that I hear is, your GPUs are just getting so much faster, so much bigger. How can I effectively utilize them? Because I've got every user, just like you've got every SA that wants their own station. but I can't give everyone their own setup. How do I do this cost effectively? And MIG is tremendously beneficial there. That's the number one conversation that I have. And it's super useful in the platform. It just looks like another GPU device to you. So you don't have to change your software programming model. You can go from a very small MIG to the very largest supercomputer, and you don't need to change your software that you're developing on. So it's just a tremendous feature.
Yeah, I have to say, Charlie, that MIG really exceeded my expectations in customer adoption. Of course, it's a new feature that came out just earlier this year with our A100 GPU architecture, and I thought it'd have slow adoption. But from university computing centers all the way up to supercomputing centers, they're not using the whole system 100% of the time to run one big problem. So being able to take every GPU and carve it up, as you said, into as many as 7 GPU instances has just been a great differentiator for that product. Unfortunately, we've run out of time. But before we end, I wanted to remind you of a few things. You don't need to wait until supercomputing next year to hear more from us. We'll be active all week at the show. So if you want to know what's going on in different sessions or visit our online booth, please go to nvidia.com/SC20. And you can see everything that's going on at the show there through that website. So thank you very much. Thank you to our speakers, Ian, Charlie, and Michael. It was a great show, and I can't wait to be back here in a year and see all of the advances in science during the next 12 months. So thank you for joining.
Thanks, everyone.
Bye.